Hi, everyone. I'm Gabby Fisher. I am a systems engineer on the Cloudflare Workers team, which I joined really recently, and I'm very excited about. And today I'm excited to talk to you about Go and its support of WebAssembly and how we can now run Go in browsers and cool new environments. So, in this talk, I'll start with an overview of why we most often see Go code in servers. I'll then introduce WebAssembly, which you all already know about, but I might as well do a little brief overview of it. Um, and then afterwards, I'll describe how Go's current tooling for WebAssembly works. And I'll go through some demos of Go and WebAssembly in action. And then I'll then conclude my talk with my thoughts on like the path forward for Go and WebAssembly and how Go's support of this instruction format can evolve. So when I think of Gophers, I think we subconsciously often think of whales as well. That's because Go and Docker are very commonly used together. So the typical process of using Go kind of looks like this. You first build it into a desired binary, which we can then run as a service in a Docker container. And then we can deploy this Docker container in an orchestration platform like Kubernetes. This common Go workflow underscores the fact that Go is most often found running on servers. After all, it's a popular language for writing services, APIs, and many other backend applications. But this does kind of beg the question, where is Go not popular? Where can't Go really go? So Go isn't really considered a client-side programming language. And this is because browsers have been the land of JavaScript for decades now. And JavaScript tends to be quite distinct from backend languages, given its use of event-based programming. And as a systems engineer who recently, well, at the time I wrote this talk, when I gave it at a conference a few months back, I had recently only really learned how to use JavaScript. I was super used to systems engineering. And I found learning JavaScript to have a pretty steep learning curve, actually. And a lot of concepts like promises were really unfamiliar to me. And it was honestly kind of telling that when I was working on learning JavaScript, I also learned that one of the backronyms for NPM is nothing prevents misery. This is literally something you can find on their website if you refresh it enough. I think this accurately described my experience when I first grappled with event-based programming and the world of Node.js. So, as an engineer who loves Go, wouldn't it be fun to write Go on browsers and minimize the amount of JavaScript I'd have to write? While knowing JavaScript is incredibly important, I could streamline my development process by using a language I already knew. There are transpilers like Gopher.js that allow me to transpile Go into JavaScript, but I still wanted to learn how I could run Go code and take advantage of its underlying runtime and other language specific properties that would have been lost if I had transpiled it to JavaScript. So that's why I'm really excited to talk about WebAssembly today. As you all know, WebAssembly is a binary instruction format built to run on browsers, agnostic of whatever operating system or architecture the browser is running on. I'm also pretty excited about WebAssembly because it's a big stride. It's the first new binary instruction format to be introduced and used in production in over 30 years. And it aims to eliminate the operating system and architecture lock-in that previous assembly languages required. Um, I feel like I'm just explaining WebAssembly to people who already know what I'm talking about, but I'll make sure to do it anyways. So it's supported by all major browsers and their respective JavaScript engines. And because it's a binary instruction format that theoretically any language can compile to, any language that can compile into WASM can now run in any browser or any major browser, that is. So to answer my earlier question about how to run Go client side, I could compile my Go into WebAssembly and run WebAssembly in a browser's JavaScript engine. This depends on Go, however, supporting WASM compilation. The good news is that Go 1.11 introduced WASM compilation and additional tooling for running Go compiled in the WebAssembly. We can now let the Gopher out of the container, so to speak, and run it in a couple of cool new places. So there are three main parts of the new tooling introduced for WASM support in Go 1.11. The first is a new standard library package, syscall.js, that provides support for passing variables and functions between Go and JavaScript. The second is a new Go compiler target that lets you compile Go into WebAssembly. And the third is some glue code that interfaces between Go compiled into WASM and the JavaScript code that calls it. Before we dive into some examples, I want to provide a disclaimer. The code I'm about to show you is still considered experimental, and this is because WebAssembly support is currently exempt from the Go compatibility promise, so future Go WebAssembly tooling could break the examples I share today. And in fact, I'm pretty sure one of the examples I'm sharing today will be broken in Go 1.13 when that's released later this year. So let's start our tour of Go's WebAssembly support with the syscall.js package. This package provides functions with which Go can access JavaScript variables and functions. It also provides functionality for exposing Go functions to JavaScript. The code I demonstrate today will either have a Gopher or a JavaScript logo on the bottom right-hand corner, just so we don't get confused between which languages I'm referencing at any time. So in this first example, I'm using Go's syscall.js package to access JavaScript values and call JavaScript functions. Here, we can see that this package lets us get global JavaScript variables, like the entire document object model, or DOM. We can also call JavaScript functions like getElementById to get specific elements in the DOM. In this case, we're going to get the element hello text. And then we can also set values in the DOM. So here I'm actually writing Go was here into the HTML of the hello text element, because Go was actually there editing JavaScript using the syscall.js library. Now let's take a cue from Missy Elliott and flip it and reverse it. Here is an example of how to set up Go so that it can be called from JavaScript. In this case, let's implement a simple add function in Go that can be called from JavaScript. This add function will take a list of JavaScript numbers from a JavaScript argument array and add them and return the sum. All functions that are called from Go need to have the function signature seen here to access JavaScript class fields, as well as accept arguments from JavaScript. The empty interface return type is also required here, though I personally think we should return js.value types so that we have symmetry between JavaScript typed arguments and JavaScript typed return values. When we receive an array of JavaScript arguments, these arguments are still in the form of JavaScript values. So we need to call the int function from the syscall.js library, so we can convert these JavaScript number types into their corresponding Go integers, so that we can actually perform operations on them in Go. If another JavaScript type, like a string, is passed, calling int would panic. So when we return a sum to JavaScript, a really important task here is that we need to convert it back into a JavaScript type. This is achieved by calling value of, which can actually infer from the Go type passed into it the type of JavaScript variable that needs to be returned to JavaScript. So you can see here that this is just basically the boilerplate for creating a Go WebAssembly function that can be integrated with JavaScript and the necessary conversions from JavaScript types to Go types and back. This isn't all though. There are a few more steps before we can actually expose this Go functionality through WASM to a JavaScript caller. So something we need to do is take our add function and call the func of function surfaced by the syscall.js library to wrap add into add func. This is basically taking our Go function and turning it into a JavaScript function and exposing that. Func of actually also calls value of on the return function to convert it into a JavaScript type. So this is just basically a way to ensure that if you're going to have a function in Go exposed to JavaScript, you are making sure that your Go values are converted into JavaScript types. So then we set the add variable in our JavaScript environment to add func. And in effect, we're saying to like the DOM, for example, we want the add value to be equivalent to the add function that we wrote in Go. The add func function is then stored in shared global memory between JavaScript and the Go WebAssembly. We should also make sure to free up this global memory used by this function by calling release when we're done using this function written in Go that's exposed to JavaScript. And finally, you're probably curious about this done channel I have at the very end here. I set up a channel that's read but never written to because we need to make sure that this Go script actually stays alive such that this exposed add function to the JavaScript environment remains there. If we were to let this function exit, that add function would actually become an undefined in JavaScript, and we wouldn't be able to use the functionality we had written in Go and exposed to WebAssembly. So it's really important to keep this exposing function open. There are multiple ways to do this though. Like if you're a Gopher, you probably might be thinking you could use an empty select or any other way of keeping the main function alive. This is just an example I used because it's what most people on GitHub tend to be doing. So I didn't want to do anything too out of left field. So that's talked about. So with this Go setup, calling a Go function from JavaScript becomes really simple in JavaScript land. Calling add is no different than calling it as if it were written in pure JavaScript. This Go add function, however, would not just work out of the box in JavaScript. There's a little more setup required, and it involves the WASM exec.js utility file, which I'll cover soon. Now that we've written Go code that is able to compile into WebAssembly and be accessed by JavaScript, we actually need to compile it into a WASM binary using the new WASM compiler target. Compiling in the WASM with Go is quite straightforward. It's a lot like compiling Go for any specific operating system and architecture. Here, the operating system just is defined as JavaScript, and the architecture is defined as WebAssembly. Now, with our compiled Go into WASM, we can properly instantiate it and expose it in the browser environment. This is where the WASM exec.js file comes in. This file is found in the misc/wasm directory of the Go language repo. Its primary purpose is to expose a Go class that can be called from JavaScript to initialize and run the Go runtime. This is a file you're supposed to just import into your JavaScript code so you can instantiate the Go class. And let's briefly take a look at what is actually in this file. The Go class here is used to specify Go environment variables that configure the runtime. So for example, one can pass in Go debug, which controls debugging variables within the runtime. It also gracefully handles exit codes from the Go runtime and logs them to the JavaScript console. This Go class also has an import object field. This is used to provide the JavaScript side functionality that the syscall.js library for Go requires. So a syscall.js function like js.set uses this value set function to find an import object to actually access and set the JavaScript value. Import object also provides other glue functions, such as one that lets log statements print to console log on the browser console or JavaScript console. So this helps basically bridge some actions in Go, like calling log, and have them actually appear on your browser console. And finally, the Go class has a run function that takes a Go WASM instance as its argument and actually runs it. This function must be called to load our desired WebAssembly binary, load global memory references, and maintain states, like whether the WASM binary has exited or not. So here's where wasm exec.js is used to load the add function we had written earlier. So the first thing we need to do is initialize the Go class. We then invoke the WebAssembly.instantiate streaming function, whose arguments are the WASM binary and the Go class's glue code stored in import object. This instantiate streaming function loads the WASM instance we seek to run. We then call go run on our loaded instance of WebAssembly code to execute it. And after the setup, we can now call our add function that we wrote in Go and compiled in WASM. I'm now going to show a browser demo of Go WASM binary that takes images from JavaScript code, grayscales them, and returns them for the JavaScript code to display. So before I show this demo, I want to give a brief overview of what's happening in this code. And we're just going to kind of gloss over what's up on the screen. So the image transformation code we use in this demo to make an image grayscale is honestly quite similar to our add function. On the left is a function called grayImage that takes a JavaScript byte array as an argument. This JavaScript byte array must store the bytes of an image we want to grayscale, and then this Go code converts it into a Go byte array. The image source bytes are then grayscaled with the image package in the Go standard library. So I'm just going to gloss over that. Assume that it turns all of those bytes into grayscaled versions of themselves. And then with these transform bytes, we convert them back into a JavaScript array and return that JavaScript array of the grayscaled bytes. On the right, this is exactly like the setup we had for our add function. We're just exposing the grayscale function using the same logic that we had covered earlier. So let's take a look at this in action. So we could see that I just logged whether WASM was initialized or not. And I wrote some boilerplate code that lets me upload a file. I'm going to take this Calico cat, upload it to our page, and you can see that our Go code was able to grayscale that. Just to show that you can do this for multiple images and that this function's exposed, like the grayscale function is exposed continuously. I'll do it on another photo. That cat is staring into your soul. So that's one example of how you can actually use Go WebAssembly to create some cool web applications. And in that demo, we saw that WebAssembly was quickly loaded and executed, even for relatively intensive image processing tasks. This quick loading is intrinsic to the architecture of browser engines because they're meant to load and run third-party code as quickly as possible for a streamlined browsing experience. These browser engines run third-party code without the overhead of tasks like container cold starts. So if WebAssembly can be loaded and executed quickly, doesn't that sound like a neat way to run third-party functions on servers? Um, so that kind of is like our segue into my next set of demos. And the segue into the beyond the browser part of this talk title. Fast WebAssembly loading and execution is precisely why companies like Cloudflare and Fastly have pursued WebAssembly execution as the future of functions as a service. Cloudflare Workers and Fastly Lucet are two examples of projects building this WASM on the server ecosystem. This is a really simplified chart comparing the stack necessary to run container-based functions as a service versus those based on browser engines. The primary difference is that instead of running code on containers, we run it on browser engines like Chrome's V8 engine. This is basically a very quick, this is going to be a quick overview of like a full talk that Kenton Varda's given at InfoQ about the architecture of these WebAssembly and browser engine based functions as a service. So if you're looking for more in-depth detail, I would go to that talk, but I'll give a really small overview of that right now. So by running third-party code as WebAssembly on servers, it's possible to offer a faster alternative to services like AWS Lambda and GCP functions, which depend on containers to load and execute third-party code. Because container cold start can take up to 500 milliseconds, cutting out this cold start can substantially speed up calls to functions as a service. Browser engines, however, currently have you bundle runtime language with WASM binaries, which still adds a lot of overhead. I really like talking to my colleague Ashley Williams, a Rust WASM working group member and maintainer, about possible approaches to address this additional bloat. She's brought up some great ideas for addressing this, like sharing language runtimes between WASM instances and potentially using dynamic linking instead of static linking to reduce the size of the binaries loaded and executed by the browser. So here's a demo of me using Go to expose an API endpoint for grayscaling a photo, similar to the browser example that I showed earlier. This is done on Cloudflare Workers, our functions as a service product. And it is pretty similar to Lambda, except where it doesn't require container cold starts and can execute third-party code faster by using the V8 engine. Okay, so this endpoint that's going to show up. Okay, actually first I'm just deploying my worker that uses Go WebAssembly. And the endpoint I deploy expects a query URL parameter that's basically just the endpoint of an image you'd like to grayscale. So of course I'm going to use cats again for this example. I'm going to pass in a cat image from the internet. And I'm going to grayscale that using a Cloudflare worker. So you could see that I was able to create a function as a service that exposes a similar function to the one I showed earlier, but this is actually running on server-side WASM now, and is able to transform images that way. You get a bonus cat. And also I do have the, oh, you can't see that. I have the domain gabbi.fish, which I'm really proud of. So this is where the problems with Go WebAssembly kind of come to light. So when I was experimenting with Go WebAssembly and Cloudflare Workers, one of my friends from the business intelligence team messaged me being like, your workers are like the third most intensive in terms of amount of CPU usage per call. What are you doing? So the thing about Go WebAssembly workers is that that bloat I described earlier is a serious problem. It makes Go WebAssembly not as fast to load and run as we would hope. And there are a lot of places where I think Go has an opportunity to streamline how it compiles in the WASM and can be loaded and executed. So before I go into what I think the future of Go's WebAssembly support should look like, I do want to talk about some examples of where Go WebAssembly can still be useful and why we should pursue this as something we'd like to optimize and improve. So what got me interested in Go WebAssembly workers in the first place was a project that I was working on a few months back. And this project required me to use a Google maintained Go library for transforming HTML. So you could see that this is a really substantial library. And I wanted to run this in the Cloudflare workers environment. And to convert all of this into JavaScript would be a pretty difficult task. Even with a transpiler like Gopher.js, there are a lot of Go-specific constructs here, kind of like wait groups that don't really cleanly map the JavaScript logic. So Gopher.js was not really an option for us in this case. So instead of rewriting all of this Go code in the JavaScript, which would have been really hard and based off of an actively maintained branch, so really hard to maintain, we decided to compile it into WebAssembly instead and run that in a worker. So this is one case where WebAssembly can be really useful for maintaining consistent code bases across client-side code and server-side code. You can run Go, for example, on the server side, but also on the client side, and maintain consistent structures between the two sides of the application you maintain. So Go WebAssembly has been useful to me. There are cases where it can be really helpful for streamlining my job. But the thing about Go WebAssembly is that it's still being actively developed. A lot of core features still need to be built out. And here are some places where I think that we can improve the Go WebAssembly ecosystem. So first of all, best practices are still unknown. It's unclear whether calling JavaScript from Go or calling Go from JavaScript is the best approach to leveraging Go's support of WebAssembly. Perhaps Go WebAssembly could draw inspiration from manuals like the one for Rust's WASM support. Rust has a really well built out WASM ecosystem, and I think Go has a lot to learn from that. Memory usage in Go WebAssembly also needs to be more efficient. Go currently asks for a gigabyte of heap memory, which is unnecessarily large when running small third-party applications. I think this is going to be fixed in Go 1.13. I saw a recent CL that actually minimizes that down to 16 megabytes, which is a huge improvement. Another thing that still needs to be addressed, though, is the fact that garbage collection doesn't exist for Go WebAssembly, and in the long run, that's something that support for WebAssembly really needs to implement. And there are some experimental branches of Go that use smaller amounts of heap memory and implement simple GC for Go WebAssembly. Devin Mullins at Google and I had worked on one that we ended up using for a Go worker with Cloudflare workers. And finally, WASM compiled to Go has very large binary sizes because the currently like the entire Go runtime is bundled into a WASM binary. I touched on this issue before, but I want to reiterate that I think the shared runtime approach is the best way to solve this, and will be the future of not just Go and WebAssembly, but I think the WebAssembly ecosystem overall. And with that, we come to the conclusion of this talk. I hope you're excited about Go's support of WebAssembly and how that empowers Go programmers to consider uses of Go beyond just server-side programming. I hope you also see opportunities to experiment with Go and WebAssembly. And finally, I'm really excited to see what you build with Go and WebAssembly. A lot of people have been very active in this field. And I was recently at GopherCon and saw some really cool applications using Go and WebAssembly. Like someone made a version of Flappy Bird, but with a Gopher in WebAssembly and ran it in the browser. That was pretty neat. There's a lot of space to grow here, and I'm hoping that the more people engage with Go WebAssembly, the more the Go language will prioritize basically making it a more fully supported feature that can be used in production systems. So thank you. And the obligatory QR code for checking out Cloudflare Workers, which is a product that I really enjoy using and working on. Thank you so much. Yeah, sure. I have time for questions. If anyone has questions.
Oh, let's ask them in the mic so we can get it on the recording.
What's the cold start time for a Go-based worker on Cloudflare?
We were going to use it in production for like a service I was working on called Ampreal URL. It ultimately was way too slow. I think that like loading and executing the WASM took like the order of seconds, which is unacceptable. So there's a lot of improvement here, and I'm really hoping to see approaches to that in the future. Other questions?
So I saw that the image package just worked directly in WebAssembly. I assume that other things would not, like the OS package probably wouldn't translate very well into WebAssembly. Anything that deals with files and other things like that. A, how do you tell what's going to work and what isn't? And B, what is the story with trying to add additional packages that can work in WebAssembly?
Experimented with any OS libraries in WebAssembly. I get the feeling that this is kind of an untold and unprodded story at the moment, but I'm curious to see what like the WebAssembly system interface, the WASI project, will do for this. At the moment, I would hazard a guess that it would not really work with Go OS libraries at least, but with the development of WASI, I think that story will change. Oh yeah, do things like break groups and channels and locks and Go work out of the box? They actually do. I've been able to use those in Go WebAssembly because that library I showed you earlier, that Google AMP transform library, actively used all of those. And they compiled and worked fine, which I was surprised but also very happy to see. So like I think that that feature is built out, but that being said, it still is quite slow to run.
Thanks for the talk. Is there a way to generate automatically the bindings between the JS and Go? I know it's the case, for example, for Scripton, you have you can make a file with the bindings telling this is the classes from C++ and they are generated for JavaScript. That's something in Go? So let's say that you have a big library in Go, and it might be a bit of work to expose all the classes that you have in Go. Is that a thing in Go? And if you have multiple functions, that might be a lot of work to write all the, you know, the code, the glue code between Go and JavaScript. So
sorry, I need coffee. Like, so I believe the question was like, if you are writing Go and JavaScript code, like how much would you want to divide writing functions in between the two languages, that balance between the two? And it really depends. I think the magic of this is that you can use JavaScript for what it's best at and only drop in Go support when it's really necessary for specific functions. You're not necessarily forced to write everything in Go or everything in JavaScript. You can really interface the two and just make sure to expose Go functions to JavaScript as needed. So I really enjoy that flexibility. And I wonder how the use patterns are going to evolve over time. But I think this flexibility is something that should be maintained. Hi.
Run off all that pizza.
So I think this is pretty closely related to the question that was just asked, but in Go, the functions that you showed written had a very specific signature. They accepted this object and they returned an interface that we sort of accept a contract like this must be js.value of something. This is not necessary in all languages. I think that Emscripten can infer the bindings, so you can use just native C++ types there. And in Rust, you can use WASM bindgen to just write Rust types, and it will sort of generate that boilerplate adapter code. How far off is that for Go? Is it even possible, given Go's type system, to automatically generate bindings like that?
I think my voice is loud enough. I think to an extent, Go actually automatically generates the return types for you. I just chose to be explicit in my code to show that that function exists. But that empty interface return type in Go is used to say like you can pass anything in. And yeah, under the hood, what happens is that like every time you return from a function with that specific function signature, the wrapping func of function that I mentioned earlier will actually infer, okay, what's the return type here? Match that type and then return the appropriate JavaScript type for that. So you don't have to be as explicit as I was, but because I wish it were a little more explicit so people knew what was really going on when writing it, because there's kind of just like some magic that like, yeah, it automatically does the bindings for you. But I feel like it would be better to keep people in the loop about what's actually going on. But that's just my design decision, you know.
Any more questions? All right, round of applause for Gabbi. Thanks again.